Hello everyone, my name is Himanshu Sharma. I'm an assistant professor in the Department of Chemical Engineering at the Indian Institute of Technology, Kanpur. And in this presentation, I will be talking about geochemical interactions in alkali surfactant polymer flooding. And before I begin, I would like to mention that whatever results that I'll be showing in this presentation, that work was conducted at the University of Texas at Austin, where I was a PhD student as well as a postdoctoral fellow. So when you think about geochemical reactions in the subsurface, you can think of this as a reaction between different species. So you can have species in the oleic phase, for example, organic acids and bases. Similarly, in the gaseous phase, you can have gases like CO2 and H2S. In the aqueous phase, you can, of course, you have some ions, but in the case of ASP flooding, you also have alkali surfactants and polymers. And last but not the least, the rock itself is made up of different minerals. For example, in carbonates you have minerals such as calcite and dolomite. In sandstone we have silica and clays, and in addition you can have other minerals in small amounts such as siderite and anhydride. And when these phases come into contact, the species that are present in these different phases uh, react, and in most cases, in some cases these reactions uh, can be unfavorable, and that can lead to changes in porosity and permeability. But even otherwise, these interactions can change the composition of the injected fluid. So the composition that is actually present in the ground can be different from the composition that you inject. Alternatively, the composition of the produced fluids can be different than the fluids that are actually present in the subsurface. And similarly, these interactions can also lead to changes in interfacial tension as well as wettability. So therefore, understanding the role of these geochemical interactions in EOR processes become important. So here I'm just giving you a brief background of ASP flooding. I'm sure most of you are aware of this. After water flooding, so after primary and secondary flooding, you leave about 50 to 70% of oil due to high interfacial tension between oil and water, as well as reservoir heterogeneity and viscous fingering. And many lab studies and field trials have shown that ASP flooding is very effective in recovering this oil that is left behind after primary and secondary flooding. ASP flooding, so these are the components of ASP flooding that I'm sure all of you are aware of. We have surfactants that lowers the interfacial tension between oil with oil, and that helps in improving the microscopic sweep efficiency. We have a polymer that provides you the favorable mobility ratio and increases the macroscopic sweep efficiency. And then you have an alkali that lowers surfactant absorption and generates in-situ soap. So in my presentation, I'll be mostly talking about interactions of alkali in the subsurface. So what are some of the advantages and challenges of an alkali? Uh, the first advantage is that when you use an alkali, it can lower the adsorption of anionic surfactants on rock surface. And that is because when you increase the pH, your rock becomes negatively charged. So that I'm showing you by this reaction. You can also see that here I'm showing you zeta potential as a function of pH of a particular rock, and you can see that the zeta potential becomes more negative as you increase the pH, and that leads to lower surfactant adsorption that is shown here. So here I'm showing surfactant adsorption without any alkali and with alkali, and you can see that the adsorption is lower when you add an alkali, and that is because now your surfaces are more negatively charged at a higher pH. Second, the alkali also generates in situ surfactant if your oil is acidic, and that is advantageous because when you generate soap in situ, then the amount of synthetic surfactants that is needed that get reduced. And the third is that these are the main, but Surfactants also help in stabilizing some of the the alkali also help in stabilizing some of the surfactants, such as sulfate surfactants. So at temperatures more than 60 degrees, increasing the alkali can stabilize uh, the sulfate surfactants. So these are some of the advantages. What are the challenges? Of course, you need water softening when you're using an alkali, because otherwise your divalent cations can precipitate. Some of these alkalis, and under some conditions, they can undergo unfavorable geochemical interactions, and that can lead to scaling at the production well, permeability damage, excessive alkali consumption, and pH propagation delays. And for field operation, since a large amount of alkali is typically needed for a field operation, storage and handling is also a challenge. Now, what are some of the characteristics of a sort of an ideal alkali? One is that it should provide you a high pH, more than 10, so that you can lower the surfactant absorption, and the alkali can generate soap in situ. In addition, your alkali should be able to propagate a high pH through the porous media without causing changes to the properties of the porous media, so without undergoing any reactions or changing the permeability. Now, in 1970s and 80s, most of the alkalis that were studied, they were fairly strong alkalis, such as sodium hydroxide, potassium hydroxide, sodium silicate. These alkalis provide a very high pH, more than 12, in some cases 13, and as a result of which these alkali undergo excessive reactions uh, with the rock. Most of these studies were performed in sandstone rocks, although some were also performed in carbonates. And what these studies found that these alkalis are too strong for an ASP flooding. These, due to these reactions, you can expect pH propagation delays, excessive alkali consumption, permeability damage, and so on. So therefore, people have now started moving towards a milder or mild alkalis, and sodium carbonate is an example of that. So with sodium carbonate, you get a pH of about 11 when you add 1 weight% sodium carbonate, and sodium carbonate is found to be effective in lowering surfactant absorption as well as surfactant absorption in both sandstone and carbonates, as well as form in situ soap in case of acidic crude oils. The reaction of sodium carbonate is much less compared to the strong alkalis, and there is one exception that I'll discuss in the following slides. In addition, sodium carbonate precipitates divalent cations, so you need water softening, but then you can also expect divalent cation precipitation when you inject this alkali in a reservoir that is a formation brine with high amount of or with the divalent cations. And these precipitations can also lead to changes in permeability. So that is one thing to keep in mind. Similarly, sodium metaborate is another alkali that we have studied recently, and the kind of pH that you get is around 10.5 with 1 weight% sodium metaborate. And sodium metaborate is somewhat tolerant to divalent ions, divalent cations. Now, this is not a very high concentration, but compared to sodium carbonate, it has more tolerance to divalent cations. That you can also see here. This was one of the experiments that we did, where we started with a 2000 ppm calcium in DI water, and we increased the amount of sodium metaborate. So here I'm just showing the boron concentration, and we found that as you increase the concentration of sodium metaborate, your calcium starts to precipitate. But so these are equilibrium concentrations. So even after precipitation, you can see some amount of calcium remains soluble. So therefore, sodium metaborate has uh, somewhat higher tolerance to divalent cations. We also found that sodium metaborate is effective in lowering adsorption on sandstone and carbonates, almost same as sodium carbonate. So that is what I'm showing here. This is the static adsorption test that we performed, and we found that, so these are three tests. One is without an alkali, and these two are with 5000 ppm sodium metaborate and sodium carbonate, and we found that we saw reduction in surfactant absorption both with sodium metaborate and sodium carbonate, and the adsorption values that we found in presence of these two alkalis were very similar. And also sodium metabolite can generate in situ soap with acidic crude oils. Then ammonia is also an alkali that we studied recently, and one of the advantages of ammonia is that it gives you a high pH with a small amount of alkali needed, and that is because ammonia has a low molecular weight compared to sodium carbonate. So you need a less amount of ammonia. It is found to lower adsorption in sandstone and carbonates, similar to similar to sodium carbonate that you can see here. With ammonia and sodium carbonate, you get lower adsorption, and it generates in situ soap with acidic crude oils. However, ammonia does not precipitate calcium ions, unlike sodium carbonate. And we'll see what are the implications of that. So here I'm showing you results from this study, these three plots, where they found that by adding ammonia, uh, as the pH increases, the surfactant absorption goes down. However, because ammonia does not precipitate calcium ions, as the calcium concentration increases, you can see that the adsorption or the retention also increases. Right, so these calcium ions that are soluble in ammonia interact with the surfactant and increases the adsorption of surfactants. So there are two effects. pH on the other hand is trying to lower adsorption, but calcium ions increase adsorption, and that is because when you increase the calcium ions, your rock becomes more positively charged, and that results in increasing the surfactant adsorption. Now, most of the previous studies were performed in sandstone. However, some studies are now also recently performed in carbonates, and that is because carbonates are typically at higher temperature and higher salinity. That is a challenging to find surfactants that can work under these conditions. They have low permeability, they are highly heterogeneous, and they have a complex mineralogy. Particularly, although calcite and dolomites are not very that soluble, but anhydrite is fairly soluble, and that makes it difficult for ASP flooding to apply on carbonate reservoirs. And what are the challenges of anhydrite? So anhydrite is fairly soluble in water. So if you inject DI water in a reservoir that has anhydrite, then you can expect about 1000 to 2000 ppm of calcium coming from the rock due to anhydrite dissolution. So that is a high amount of calcium that you get from the rock. And in presence of alkali, you can expect that these calcium ions interact with the, for example, in case of sodium carbonate, reacts with carbonate ions and precipitates the calcium carbonate. And this reaction continues until either the alkali is finished or the anhydrite is finished. Similarly, if you have sodium hydroxide, then you form calcium hydroxide. So because of these precipitation, you have alkali consumption, your pH propagation is delayed, and so on and so forth. What is more worrying is that even a small amount of anhydrite, as low as 0.18%, which is difficult to detect from XRD analysis, is enough to cause severe damage to your ASP flooding. So we did some experiments where we studied the experiments and simulations to study the impact of injecting sodium carbonate in rocks that have gypsum. So these are carbonate rocks with gypsum, and as you would expect that when you add sodium carbonate, you would expect a precipitation of calcium carbonate in presence of sodium carbonate. And that is what I'm showing here. So these are the simulation plots where I'm plotting the effluent pH as a function of pore volume for two cases. In the first case, when you do not have any gypsum, then your pH comes out to be same as the injected pH, around 11. On the other hand, if you have gypsum, then the effluent pH goes down to about 9, and that is because of this precipitation reaction that is going on. So you have high alkali consumption, pH propagation delays, and in this experiment that we conducted, we found that the rock becomes completely plugged because of these precipitation reaction. Then we also looked at the effluent ions, and we found that because of this reaction, the sulfate concentration increases to a very high value. So here in the effluents, we were measuring sulfate as high as 23 or 24,000 ppm, although we did not inject any sulfate in the injection brine because the injection brine had only sodium carbonate and sodium chloride. So this sulfate is coming from the dissolution of anhydride and the precipitation of calcium carbonate. And we did not see any calcium ions because although you when sodium this anhydride is dissolving, you would expect some calcium, but that precipitates because of sodium carbonate, and therefore we did not see any calcium in the effluents. We repeated similar studies with sodium metaborate, same core or a similar core with gypsum or anhydride, and we found that sodium metaborate was able to propagate the pH, a high pH around 10.2 at about 1 pore volume 1.5 itself. Our pH was about 10.2, and the extent of reaction was much less severe compared to sodium carbonate. As you can see that the calcium concentration is around 300 ppm, and the sulfate is also around 2 to 3000 ppm, not as high as 23,000 or 24,000 ppm that we saw in the case of sodium carbonate. Similarly, we also performed a test where we injected ammonia in presence of anhydride, and we found that since ammonia has tolerance for calcium ions, we saw very good pH propagation. So at 1.5 pore volume injection, our pH was already similar to the injected pH of about 11, and our sulfate and calcium ions were in equimolar amount. So that means we did not see any precipitation when we injected ammonia. So at least we found that ammonia and metaborate, sodium metaborate, are better in terms of propagating the pH, although this does not automatically translates into a lower surfactant absorption. So more studies are needed to confirm that. Now there's one more point that I wanted to mention, that is that although interaction of alkali is important, but these geochemical interactions are also important for surfactant phase behavior and polymer stability. So you can, for example, we saw that when you have anhydride in your reservoir, then you can expect about 500 to 2000 ppm calcium ions. And therefore, if you do not have any calcium ion in your surfactant slug, then calcium as high as 2000 ppm can come from the rock due to anhydride dissolution, and that can affect your surfactant phase behavior. So if your surfactants are not tolerant to hardness, then you would lose ultra low IFT. Also, because of these divalent cations, there may be a shift in the optimum salinity that I'm showing you here. So here I'm showing you solubilization ratio as a function of TDS. So this is the optimum salinity when you do not have any calcium, and the solubilization ratio is about 12 uh, when you don't have any calcium. But then when you add calcium, 1000 ppm, you can see that the optimum salinity shifts to around 45,000 ppm, and your solubilization ratio also goes down slightly to about 11. But what is more worrying is that your change in optimum salinity is about 20,000 ppm, and therefore if you design your ASP flood according to this phase behavior, then you can expect that your experiment or your uh, uh, study will not be effective because your actual phase behavior is different. So therefore it's important to consider the effect of these interactions, particularly in case of anhydride, not just on alkali but also on surfactant phase behavior, but also on polymer stability, because some polymers are not tolerant to hardness, particularly if the degree of hydrolysis is very high for a polymer, for an acrylamide polymer. So with that, in summary, we know that alkalis are useful because they can lower surfactant absorption and generate in situ soap. But strong alkalis or the alkalis that exhibit excessive reaction with the rock can be detrimental for ASP flooding because they can cause permeability damage, excessive alkali consumption, pH propagation delays, and so on. And therefore, it is important to consider rock mineralogy when designing an ASP flood. And recent studies have found that sodium carbonate, sodium metaborate, and ammonia are better compared to the strong alkalis that were used in the 70s and 80s. And last but not the least, the effect of geochemical interaction on surfactant phase behavior and polymer stability is equally important. These are some of the references that the results that I showed in this presentation. And I would like to acknowledge Dr. Kishore Mohanty, Dr. Gary Pope, and Dr. Upali Veera Surya, who were my uh, PhD supervisors, as well as I worked with them during my postdoctoral fellow in the Department of Petroleum Engineering at the University of Texas at Austin. And thank you very much. And I'll be happy to answer any questions you may have. Thank you.